gentlemen,
That's recording. Has begun.
has begun. All right.
Sorry.
Last week, the first part of chapter 6, we talked about the concept of work. And we talked about what work was and what work wasn't and what work did. And we said that generally we talk about work being a change in the energy of an object. But we only gave a real brief definition of what energy was. And we said that energy is the ability to change things, the ability to make things different. In section 6.2, we start looking at the relationship between work and energy, and how does work change the energy of an object? What is it about that object that it is changing that results in something new, that results in it being able to do something different than it did before? So the first thing we talk about is kinetic energy, and I think that most of you probably are aware that kinetic energy is the energy of motion. By virtue of the fact that something is moving, it has the ability to move or change or make something different than it did before. This ball, as it sits here on the desk, it's really no danger to anybody, right? But if I started moving, now it has that ability to change things, to hit you in the head and split your head open or whatever it is, okay, right? But that doesn't happen until it starts moving. So this part here that shows up on your first page, and I'm not going to hold you responsible for this, but just so you kind of see where it all comes from. Zoom in here so you can see it a little bit better. Okay. All right, up at the top, we start with a kinematic equation. It's a kinematic equation that we used before, right? Here it is. Vf squared equals vi squared plus 2a times delta x. This says d, but that says delta x. Same, I think, and the smiley face. Yeah, I'm not sure who put the smiley face up there, but it's been there for a while. I don't remember. Next line, just do a little rearranging. Subtract vi from both sides. And then they flipped it. I'm not really sure why they did that, but they did. So, yeah. Then, in the previous chapter, right, we learned that Newton's second law deals with acceleration, that F equals ma. But we can rearrange that equation to get a by itself, no biggie. But now that we know that this is a, we can substitute this expression into this equation. They do that, and they end up with this equation right here. The left-hand side of this equation, I hope, looks familiar. All right? What is the left-hand side of that equation that I just circled in red? It's force times distance, which we learned last week is how we calculate what? Work, right? So the left-hand side of this equation is equal to the work that is done in a situation. And we can see here that that work influences this expression of 1/2 mv squared. This expression here that describes some aspect of an object. That work affects this quantity. How do we know it affects this quantity? Because we see here final, initial, right? Whenever we compare the final of something and the initial of something, what are we looking at? If we look at what it started at and what it ends up at, well, displacement is a kind of what? More general, we look at the change in something, right? So this side over here is looking at the change in something. Displacement being a change in position, right? So this is reflecting some kind of a change. And it's a change in this quantity, 1/2 mv squared. Okay? Don't worry, we'll put it all together here in a second. But that quantity, 1/2 mv squared, that is what we call the kinetic energy of an object. Like we've said, kinetic energy is the energy due to its motion. Because of the fact that it's moving, it has the ability to move or change something else. Right here, that's how we calculate the amount of kinetic energy that an object has. The amount of kinetic energy that an object has depends on two things. It depends on its mass, and then it also depends on its velocity. How big is that object, and then how fast is it going? You'll see here that here they say that the v is representing velocity, but up here in the paragraph right above it, it says that v is representing speed. We spent a good amount of time way back in chapter 2 talking about how speed and velocity aren't the same thing, right? That they tell you different things. But here, the author appears to be using them interchangeably. But what we find out is that here, right, in the v, what are we doing mathematically to that v term in the equation? You're squaring it. So even if you put a negative number in that formula, right, what happens? Turns out to be what? Turns out to be positive. Kinetic energy is a scalar quantity. It does not have direction. This ball would hurt you just as much if I threw it at you this way, right? Or if I went around behind you and threw it at you the other way, right? Or a car that is traveling 35 miles per hour east. A car traveling 35 miles per hour east can do just as much damage as a car traveling 35 miles per hour west. Direction does not matter when we are talking about kinetic energy. Good there? Okay. Two key concepts. How do we know they're key concept? Key, right? There it is. Oh, that's not key I wanted to, that's not what I wanted to do. Right? Key concept, right? How is the kinetic energy of an object related to its mass and velocity? So there's two factors in that equation, but what we see is that each of them affects the amount of kinetic energy an object has differently. Kinetic energy increases linearly with mass, but with the square of velocity. Okay? Meaning, let's say I have an object and it has a certain mass, mass m. And I do the calculation, the formula for kinetic energy, based on its m and its v, blah, 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 and it comes out to have some kinetic energy equal to Ke. If I take the mass and double it, I make that object twice as big. Either, I make it heavier. If it's you, I put a backpack on you that is just as heavy as you are, whatever it might be. What we would find is that the kinetic energy would also become twice as big. That if we double the mass, we double the kinetic energy. That's a linear, or we might also call it what kind of a relationship? A direct relationship, right? One goes up, the other one goes up by the same factor. But what we find out is if we take velocity and we go 2 times faster, so you're going 35 miles per hour on the road outside of school versus 70 miles per hour on the highway. The kinetic energy, wrong color. The kinetic energy would go up by a factor of 4 because it increases with the square of velocity. Right? Twice as much speed means 4 times as much kinetic energy, right? 2 squared is 4. Does that make sense? Meaning, right, if you get into a crash on Hilliard going 35 miles per hour, or you get into a crash on the highway going 70 miles per hour, how bad of a crash is the one on the highway? Is it twice as bad of a crash? No, it's what? It's 4 times as bad of a crash, right? Remember energy being that ability to change stuff or make it different. Okay? So even a small increase in speed can have a relatively large increase in energy because of that squared factor. Good there? All right, let's run through this example real quick. It doesn't get much easier than part A. So it says 3,900 kilogram truck is moving at 6 meters per second. A, what is the kinetic energy? So what is it asking us for? It wants to know what the kinetic energy is, right? It gave us some information, right? 3,900 kilograms, that's going to be the object's what? Mass. That's going to be its mass, right? So 3,900. And then moving at 6 meters per second, that's going to be the what? That's going to be the velocity. I suppose we could also say it's going to be the speed too, because what does it not tell us? It doesn't tell us which direction. So then, right, we just learned that KE is equal to 1/2 mv squared. So we start plugging in things we know, right? 1/2 is 1/2. You can't change that. It's part of the formula. If there's 2 ways that people get calculations with kinetic energy wrong. One of them is they forget to put in the 1/2. Okay? Then mass here. All right? And then the velocity. 6 meters per second. But you got to square the velocity. The other way people get calculations with kinetic energy wrong is they forget to square the velocity. So make sure you do the 1/2. Make sure you square the velocity. Just the velocity. It's not the whole thing that's squared. It's just the velocity that's squared. So you plug that in, and if I remember correctly, you get this. Is that correct? 70,200? Mm-hmm. Good there? All right. Let's take a look at some units. So here, right, unit of mass, we got the kilograms, okay? And then here with velocity, we've got meters per second, but what did we do to that meters per second unit? We squared it, right? So now it's meters squared over seconds squared. Nothing cancels there, right? There's nothing on the top and the bottom that we can cancel out. So we end up with the unit just being the combination of all those units. But earlier this, or last week, earlier in this unit, we talked about this combination of units, right? Yeah. How do we represent that combination? That's joules, okay? So that's going to be our unit as far as kinetic energy goes. Also, just to finish this off, right? 2 sig digs in this problem, right? Or sorry, 2 sig digs here, 2 sig digs here. So that means our answer is going to have 2 sig digs. That gets kind of ugly, okay? We have to do it this way because you got the 0 and you have to make it significant. And moral of that story is I won't give you this one like this on the test. So. Good there? All right, for part B, there are 2 ways that we can do part B. One is just the robotic way. One is the way that we actually think about it and make our lives maybe a little bit easier. So it says, what is the truck's kinetic energy if the speed is doubled to 12 meters per second? So we could just go through again and do the calculation, plugging 12 in for the velocity and getting an answer. But we just learned that kinetic energy increases with the square of velocity. So it says here that we're doubling the velocity. And we talked about the idea that if you double the velocity, what are you doing to the kinetic energy? How much is that going to go up? Not 2 times, 4 times, right? Because you got to square that velocity. So if we know how much kinetic energy the original one has, we can answer part B just by doing what to this number? Multiplying it by 4, right? All we have to do here, just multiply this number by 4, right? And you should end up with that, right? And if we wanted to round that, we'd probably go like that. Good there? So that gives us our first calculation dealing with kinetic energy. How do mass and velocity affect the amount of kinetic energy? The next part of this discussion centers on this little section right here where we talked about the units, especially here, right? We've come across joules already, right? What was joules the unit for? Work. But we see here that joules also shows up to be the unit for energy as well, kinetic energy. Because what we find out is that work and kinetic energy are related. Key point. Specifically, the total work done on an object equals the change in its kinetic energy. If we go back to the front page, you have this picture of this lady pushing this box, yes? Is this lady doing work on the box? Yeah, why? It's moving and she's applying a force and it moves because of her force, right? But when she does that, right, doing work on an object changes its speed. In this case, what would we see about the speed of the box? What would happen to the speed of that box? It would increase. We talked about other situations where the speed might decrease, right? If we talk about like negative work, right? But in this case, positive work, increase in speed. What we find out is that the total work done is equal to the change in the kinetic energy of that object. Work changes the kinetic energy of an object. By how much? Depends on how much work you do. We call this idea the work-energy theorem. That the amount of work that we do on an object is equal to the change in its kinetic energy. Good there? If we look at this quick example that shows up underneath, right, it says, how much work is required for a 74 kilogram sprinter to accelerate from rest to a speed of 2.2? First, right, how much work? So this question is asking us to solve for work. Now, in earlier part of this chapter, in section 1, in order to calculate the amount of work, we needed to know what? Force and distance. But if you look at this problem, does it tell you anything about the force or the distance? It doesn't. It gives you a mass, right? And then it says that tells you about the motion from rest to a speed of 2.2. What is that giving you? We could figure out acceleration, but it's actually giving you two pieces of information. It's giving you what?
Velocity.
It's giving you two velocities, actually, right? What is it giving you?
VF and VI.
VF and VI, right? Morgo, what's VI?
0.
From rest, right? And then to a speed of 2.2. this is the kind of problem that we might have done with a kinematics equation, right? Or even when we talked about like force and mass and acceleration, we might have done a problem like this too. But, like we said, it's not the kind of problems that are different, it's just the way that we address them. You don't have to write this part down, but we just learned that the amount of work is equal to the change in the kinetic energy, right? That's called the work energy theorem. We're all familiar with the concept of delta, right? Change, yes? Right? In order to calculate the change in something, what do you need to know? The start and the finish, right? So, here, we can change this equation to look like this. Right? And then we just learned that the amount of kinetic energy an object has depends on two factors. What are those two factors? What two things? Mass and velocity are the two things that determine the kinetic energy, right, Jamie? Does that make sense? Right? Now, we'll find out that those other things that you just said also will influence, but not in a direct sort of way. So we know that kinetic energy is 1/2 mv squared. If we're looking for the final kinetic energy, what velocity do you think we should use? Probably the final velocity. Minus 1/2 mv squared again. But now this time, because we're looking for the initial kinetic energy, right? Which velocity do you think we probably should use?
0.
Well, more generally the initial one, right?
Yeah.
So we start plugging in things we know. 1/2. 74 goes here. 2.2 goes here. Make sure we square that. Minus 1/2. Mass is still 74. We figured out that the initial velocity was 0. In this term on the right, we have a 0 in it, multiplying by a bunch of other things. What happens to that whole term?
0.
Right? This whole term just goes away. We don't have to worry about it right now. And that leaves us then with the amount of work just equal to this calculation for kinetic energy. And if I remember right, 179.08. So that's going to be joules, right? I wonder if that'll show up. I wonder if that'll turn up on the.
Probably not. It's a Ferris Bueller thing.
I know what it is. Then to finish this off, 2 sig digs here, 2 sig digs here. 180 joules. Margaret, did you see you've seen Ferris Bueller a little bit?
Yeah, that's what I said too.
It's worth your time. I mean, it's worth the hour and 45-minute investment of time. So.
You see that YouTube or the Super Bowl commercial? Or whatever.
The what?
The Super Bowl commercial with the Kia. It's
Yeah.
with the guy from Ferris Bueller.
No.
He's like, sometimes life passes you up, and sometimes you're gonna miss it. He's in this. He's in the Kia.
Gotcha. All right, bottom of that page, there's this problem here. It says, to accelerate a certain car from rest to the speed v requires the work w. Is the work required to accelerate the car from v to 2v equal to w, 2w, 3w, or 4w? So I know this is kind of confusing, okay? But these are the kind of questions that show up on like standardized tests, like SAT and ACT kind of stuff. These are the kind of questions that show up all the time, okay? So here's what I want you to do. I want you to take 2 minutes, and I want you to talk to the person next to you, and I want you to think about the factors that we just talked about. How does velocity affect kinetic energy? How is kinetic energy affected by work, et cetera, et cetera, et cetera, and see if you can come up with the answer to this question, okay? Let's take 1 minute, then we'll come back and discuss together. Go.
Wait, hold on. Wait, so I think it's
Because the work
wait.
keeping track of what the velocity and what the kinetic energy are of that car at those different spots. I'll tell you in a second.
I feel like it's not that easy.
You have to think about it a little bit closer than that, Jake. Think about what it's actually asking you for.
Today's a full practice. Instead of full practice.
Seven W on that.
It's like,
Might be too
It's not even possible, bro.
Because it's a changing kinetic energy, that'd be
You can block this one? It's really cute.
you like rock?
Yeah.
You're right track. All right, so let's discuss. Let's take care of our velocities here, right? It tells us that this car starts off how?
from rest.
From rest, right? So that means here, the velocity is 0. And then it goes to the speed v. So that means here, it's going v, right? And then it goes from v to 2v. So here, its velocity is twice as much, or 2v. Got that? Good? Yes? Okay. If an object isn't moving, how much kinetic energy does it have? So that means this is going to be 0 here as well. It doesn't tell us anything about the mass or the velocity of this car, other than that it's going v. So we can't really say anything about its kinetic energy, except why don't we just call it K, right? All right, let's call it KE for kinetic energy, right? But we did talk about the fact that if we double the velocity, right, what happens to the kinetic energy? It quadruples, right? Or it's 4 times as much. So that means here, there's 4 times as much kinetic energy, right? Now, this question asked us, though, about work. And we said that work is equal to the change in kinetic energy. So we can't just look at one spot to determine work. We have to look at 2 spots, right? A start and a finish. How much work is done from here to here? 1 KE, right? Or just equal to KE, right? But from here to here, right? How much of a change are we looking at there?
3K.
3 KE.
So you say 4K?
No. It would be 4 KE for the whole thing, right? But this specifically just asked you about from V to 2V. So the answer there is 3W. Okay?
Okay.
Does that make sense?
You guys get how the red from blue make purple? That too.
Got visual learners out there. Yeah. All right, tomorrow we will talk about potential energy. And we will also answer some questions dealing with kinetic energy, more work energy theorem stuff.
What's textbook?